then we'll have the practice in the class. We'll start today with the magnetic circuits. We'll finish reviewing single phase and three phase AC circuits. I hope that you got a good idea about AC circuits, especially how to calculate the current, the power, the active power, power factor, all the things. Very important. There's only one thing that I think, I don't know if I explained it or not, how to find the maximum power. So one time we're going to do the maximum power. It's important how to calculate maximum power from AC circuits. Maybe I will just go explain it when we do the. So the first topic in electric machine is still explaining the fundamentals that will help us to understand how electric machines operate. Magnetic circuits will help us to understand most of the transformer, the physics needed to explain the operation of transformer, and 50% of rotating electric machines. Because electric machines need something else, conversion from electric magnetic system into mechanical system. So today it's simple, and I believe you did that in physics. But every time I'm explaining any topic, I try to remember when I was student and what concept I was suffering, and I will try you not to suffer. So I will go through the magnetic circuit, and there are questions, and these questions came up to my mind when I'm taking physics. What is magnetic field? What is magnetic flux? Field density, field intensity. There are many things, and it's very important to understand the meaning of it. And the mathematical equations are simple to use. So what is magnetic field? What is field? This field means in general electric, magnetic, any field. What does mean field? Does field exist? You can see. The field, any field, it's what's effect. Those days when the old days in Israel, there was a bully in every region, right? Go back to the history for the police, anything like that, you'll find a bully in every region, right? And this bully controlling this region. He said that it's effect, this field effect, like this region that has his effect. It's a bad example, but it's field. So say, for example, this region for this gang, this bully, you know, so that's their field. So the effect, electric field, magnetic field, it's not materialistic thing or material thing that you can touch it, but you can see its effect. The magnetic field, if you get the magnet, any magnet, and then you put the ion filling, you'll find that start to take some pattern. So say, okay, it's the field. But actually there are lines. No, it's the field, the effect. It's the way the ion filling taking the effect of this magnet and forming lines. So say this is magnetic field. So the magnetic field, they are lines of the effect of magnet on ferromagnetic materials in general. So that's the field. What about the magnetic flux? The word, this flux used not only in field, or magnetic field used in many. How much? How much? Close? Yes. But the lines itself, it's actually the line, because flux is like, if you have fluid or anything like that, when say the flux means like the stream. So you can say that streams of something flowing. So that's the streams of the magnetic field, the lines of magnetic field, or the streams of it. What density and the intensity? You have this in physics, right? And I'm sure you know how to calculate. I gave the equation B equal mu H and all that. This is intensity, but what does it mean? What is the difference between intensity and density. So that's the magnetic field. And when you look at it, the streams of lines of magnetic field, it's imaginary. There are no lines, but these lines is the ion filling direction, the effect of it. So if we assume we can see these lines of the effect, and we have any surface, so the density lines of flux, example, every 1 meter square, how much flux? That will be the flux density. It's flux per area, not an area perpendicular to it. But you got to remember when you do the vectors, it's also I faced when I was student, they say that the vector P will be in the direction of the area. I said how come? And just the professor said perpendicular to any surface, right? Remember that you have a surface, should be perpendicular, but vectorially you'll say that they are in the same direction. Why? So then I went back and felt, okay, the direction of any area, any surface, it has a vector perpendicular to the area itself. Like if this table, if you have this table, well, when you have the direction upward, when you see P dot A. So why I'm saying P dot A? So we can find the flux. The total flux is equal to the density times the area, but not an area in the direction of the area itself. So P is the flux density. It's equal flux per area. What about the unit? Weber. The flux area meter square, when you divide Weber per meter square, you get the unit of the density, flux density, Weber per meter square, and you call it Tesla. That's the unit of the flux density. I just give you here like a picture to show you the low density and high density. That's the difference between them. You find if one has high density, you find crowded, more lines per unit area. That's the. What about intensity? What's the difference between intensity and density? I'd like somebody to tell me difference. Magnitude of the flux. The magnitude of the flux is phi. This is the magnitude. When you, that's phi. That's the magnetic flux. The total number of magnetic lines. That's the total. That's the magnetic flux. But what does it mean intensity? Strong. That's right. That's the right word. How strong is the field? Let me give you a simple example. Say if you count the lines there, you find you have 10 lines, and you have here 10 lines. So the density is the same. If you have per 1 meter square 10 lines of magnetic flux, and you have 10 lines, but they are equal density, but maybe there is one instead than the other. So it depends on the strength of it. So I think I can do it by simple picture here. You got here the same density, 3 lines per unit area, but look at the thickness of this line, how strong it is. So that's the intensity, the field intensity, the strength of magnetic field. You can have one line of magnetic field, one line magnetic field, but this one is stronger, it can attract heavy weight or more. Okay, so that's the difference between the intensity, the density, flux density, and the flux. That's the relationship between the flux and the density. As you said, that the density, it's the flux per area. If you want to find the total flux, you multiply it by the area. S is the area. Of course, you do integration if you have surface not uniform surface, if it's like a sphere or anything like that, then you do the integration. We don't do that. You did that in physics. We're not going to do that again. We're taking the simple case. So the flux is equal to the density times the area. That's in general the integration, and observe the dot. That was bottom if it dot, and the dot, yes, still perpendicular on the surface, but because the direction, look at the direction of ds of the area, perpendicular on the surface itself. In the uniform case, what does mean uniform? Means that all lines are parallel, equal. So it will be the flux density times the area and cosine theta if it's shifted. Like what means shifted? This is the direction of the. So that's how to find total flux. The intensity, it's related to the density by mu. Mu is called permeability. I'm sure you had this in, well, even you had in high school, permeability. I am cool, but just let's say, what does it mean, permeability? In English, what does it mean, this word? What does it mean? Yes, why?
Is it how resistant the material?
I know that you understand the meaning of this. Like the opposite effect? But I know, yeah, you have the right concept. This is the right concept. Somebody can explain it more, permeability. I gave you the direction. Penetrate, pass through some. If you get something, whatever the material made of it, and then you try to get it in a dough or in a wood. So in a dough, maybe it can go, penetrate and go, but maybe the wood will prevent. So you have like how much magnetic flux allowed to be, like if you have air, if you have silicon, you have steel, if you are lines, you go through this material easily, how much? Maybe you can have 10 lines, let me just make that 10 lines, and then you'll find that only 5 pass through this medium, or 2 or 0. The strange, okay, give me one metal that doesn't allow magnetic field. 10?
10.
Some alloy that you can do together that allow the magnetic flux to go through. So the permeability, it's like how much percentage allow for magnetic field to go through. And we have two, if you have in the free space, we call it mu naught, and they measure it, and it's equal to 4 pi times 10 power negative 7. It's always very small. And if you want to find mu for any material different than the free space, like iron or any other material, so the related to the free space permeability by coefficient called mu r, relative permeability. So the total mu is equal mu naught times mu r. As you see here, mu is equal mu naught mu r. The free space permeability times the relative permeability. And usually relative permeability will be like a complete integer number, like 100, 200, 500 times. Of course, it means that times mu naught. And I will show you a table in a while to show. So the relationship between the intensity and density is mu, and usually sketch as a curve for each material. Let me show you, and since we talk about it, for space, free space, it's linear relationship between H and B. Usually you do H in x-axis. How they create H? Make this test. They get core, they wrap like winding wire as a coil, and then they start supply voltage, so the current will go through the current is responsible for creating the magnetic field. So the increase the current when you the current of the magnetic field H, and then they measure B, the density. They found that it's a linear relationship. So from this curve, if you want to find the corresponding B or H, whatever, let's say that you want to have flux density equal to 1. So you go across 1, and you go there, you find H. And when you find H, then you can calculate the suitable amount of current through the coil to produce this H, which will be responsible to produce B, the flux density that you want. So in this example, if you have 1 millitesla, I'm sorry, flux density, it needs 800 of the unit of the H to have this flux density. Obviously, the relationship is linear between B and H in free space. And we know the relationship B is equal mu H. In this case, you have only the free space, mu will be equal mu naught. So you can say that B over H will be equal mu naught. And that's the slope of the straight line. It's only for free space. Go to other material. And solution is different. It's straight line. After that, starts to be saturated. Why? Why? Iron, steel, whatever we have, it's increasing. Flux increasing, flux density increasing until you reach a specific instant, and but the increase in the flux density is really small. Why?
Not being moved anymore like it is twisting.
Yeah, not, but not, I mean, not moving. Inside any material consists of electrons, group of electrons together with the protons, they form something called dipole. Dipole is like small magnet inside any material. Like if you get any material like that, you can see they have magnet inside. You don't have magnet, but the way that the electrons in the orbits are arranged, they form dipole, which is small magnet. And they are everywhere or randomly distributed. You don't have unified direction. So the magnetism inside this material is equal to 0. But when you put magnet, you put this material between magnet, or you make coil, then start to make magnetic field. So the all dipole inside the material or the little magnet will be directed in one direction. So every time you're increasing the current, you're increasing this dipole to align according to the magnetic field, take direction. But when they reach dipoles, they are already aligned in one direction. It doesn't matter if you're going to increase them, because you don't have, that's it. They got most of the dipoles, they are aligned. So in the beginning, maybe 100, then 90, 50, then you don't have 10 left. Then if everything is already aligned in one direction, if you increase the current, you can't say it's saturated. All of them you have one direction. So that's why in core or thing like that, you'll find that at certain point start to make like at the knee of the curve, and then start to saturate to be straight line, horizontal. Of course, doesn't happen in air, because air is just infinity. So it's still continue. You can do the all free space. So that's why, I mean, we get, so the mu, the relationship, and only in the linear part here, and here, in some material, they have linear parts, more region, some they have more, like steel, they have more. So B is equal mu naught mu R H. This relationship is only valid for the linear region, but after that, you can't. And that's why most of the people, the engineering, they use this curve to get exactly the relationship between B and H, because what is the value of this BH curve? to find the value of H or find the value of B when you are designing any electric machine. So they use the curve. So that's the story of the B and H. And that's, I put here the table that it will explain to you the relative permeability. Let me just remind you, mu is equal mu naught, mu R. So mu R is less than 1 in the material diamagnetic, that which doesn't allow magnetic field or magnetic flux to go through most of it. And there are examples here, I give it to you. And the paramagnetic, it's greater than 1. You'll find it's ferromagnetic, it's the most common material used in electric machine, all types of iron, because it's much greater than 1. We're talking about 100 and 1,000. It depends on the alloy that we're going to use. It allows most of the line. And that's the problem of magnetic field. You cannot get more of the magnetic field lines in the material. So that's the relationship between B and H, and that's the now we want to find the relationship between electricity and magnetism. Conductor has current to a magnetic field B, and you can find the relationship, but the one that's important to us for Ampere's law, this one. This is the important law that we're going to use. What is that? What does it mean? H dot dl equal I. You have current. Let's say if you have a core like that, made of iron, and you have a coil, and even let me just make it even if you have only one coil only, like one wire like that, I. So that will make magnetic field, and the lines will be usually you'll find in any textbook making this dot line. This is the magnetic field path. But practically, it's not only that. They make everywhere, like here, everywhere. Specific path. Because when you have conductor and you have current in it, there are magnetic field, like you can say, circle everywhere, not only in circle. So if you choose any path, the intensity of magnetic field along this path, that will be helpful. H dot dl, what means dot dl? It means that the intensity that you want to calculate should be on the line that you want to calculate. So let's say that you have here the coil, and then this is the dot line. That's what you can calculate the H. So say H dl. Well, in this case, H times L. What's L? L is the length of the path of this magnetic field. So if you consider it as a circle, so if you can get the circumference of the circle, this is L. This is the length where you want to calculate H along this path. So H times L in this case will be equal the current. HL will be the current that you have. You have 10 amp, then you will have H times L will equal 10. Use the H if you want to calculate along this path. So that's why I'm saying it's important to know Ampere's law. H dot TL means the component of the field intensity along the path that you want to calculate the field intensity. In our case, we always take it along the path and always will be in the same. So you can remove the dot now. It's in the same direction. There is no shift. So HL is equal sigma I. In the same path that you want to calculate H here. You want to calculate H along this path, and the length of this dotted circle L. So we say H times L is equal the current, but here the current, if you have, let's say I is equal 10 amp, but let's say you have 3 terms. So every term producing magnetic field intensity. So actually H times L here will be equal 30 amperes. Because each coil producing magnetic field. Second one, the same amount, because the same current. Another 3 times. So you can say now HL is equal the number of terms in times I, when you have the coil has many terms. So I brought here in this formula, why I'm making this closed integration means the path has to be closed. And magnetic field, all the lines of magnetic field, they are closed. Like if you remember, even if you have a natural magnet, north and south, you'll find that comes like that. It's always closed. Opposite to the electric field. If you have positive charge, you can just, if you remember in physics, it's coming out from here. It's not closed. The magnetic field is closed. That's why you got to close integration. But we are not going to have complicated formula. But when you say you don't make integration anymore, because we're making DL, it's L already given to us, as I will show you now. So just you have to choose closed path. That's all. So when you multiply N times I, that's producing the field, depends on the number of turns, they give it a name. If you multiply the current by the number of turns that you have in the coil, they call it F, the magnetomotive force, MMF, but we give the symbol to F. That's the magnetomotive force, MMF. It's like similar to what you learned before in generating electricity, called electromotive force. So this is magnetomotive force, MMF, and it's equal the total current, means number of turns times I. That will be equal to HL, sigma HL. So you can say that F, magnetomotive force, is equal N times I, and it's equal sigma HL. So you can say equal H L1, H1 L1, H2 L2, and so on. Whatever. Now let's see the magnetic circuit. That's a simple magnetic circuit. You have a coil, and you apply voltage E, and the number of turns N. So the broken lines here, that's the path of the H that you want to calculate. Call this HC, means the field intensity in the core. C means core. And the length of this core, that's the core mean length, because there are many lines. You think only there is line, the broken line, this is the only magnetic field inside. No, there are many. As I told you, there are infinity of lines everywhere. But for simplicity, we're going to take in the middle. We'll say, okay, all these lines will make it only one line, and this is in the middle of the core. Like, for example, if you are giving, this is 20 centimeter. So you broke it to half. So say it's 10 from here and 10 centimeters from here. Take it from the middle. From the corner in the middle, everything, just take the mean length of the LC. That's the core mean length in ferromagnetic material. What about this small circles around? Because I told you, magnetic fields everywhere. So you're trying to say to you that the magnetic field lines that are not inside the core, we call it leakage. Leakage flux. Why? Because we are not going to use it. The future, we are going to have another coil here. So we are using this magnetic field in the transformer to tie between the two coils. But this leakage doesn't affect this coil. So we call it leakage. I'm not using. So there is leakage flux, but this is the main flux that we want. And this coil, because this coil is responsible for producing the magnetic field, we call it the exciting coil. We said that the magnetomotive force, it's equal NI, it's equal according to Ampere's law, HDL. In this case, you have only one H and one L. You calculate this L, and from this you can find H, the field intensity. Will be equal NI. You have the number of turns, like 100 turns. You have 10 am or 2 am. If you have, for example, that's 10 am, and this one you have like 50 turns. So you got 500, and then the length. You find the length of this thing. How? Let's say it's equal half meter. So that will be 1,000. That's HC. Let me go back here to tell you about this table. I'm going to put in the folio. That's for the whole thing that we explain about V and H. I'm giving the unit here for everything. So the magnetic field intensity H, it's Ampere per meter. Here we go. Here, how we can calculate the H. If you want to calculate the flux density of the field of this intensity that you calculate, you know that they have a relationship between B and H. It's either you are using the curve, H curve, or if it's working on the linear region, use mu. And many problems are going to use mu for simplicity. So that's once you got H, you can get B by this relation. If you want to find phi, the flux density, and you have B, it's easy, because what's the relationship between flux and flux density? The area. So you multiply this B by area, you get what area? That's important. You got to cut this curve and look at the cross-section area. Maybe it's a circle, maybe it's a rectangle like that. If you look at it, maybe if you cut it, you find it look like that. So you calculate this area of the curve. Why I'm calculating the cross-section area? Because that's where the flux is going through the perpendicular to it. Cut this curve, look at the cross-section area, see the dimension, calculate the area. Then you calculate the total flux phi. That's phi how you get it, by multiplying by the area. So when we do that, you got B is equal mu Ni from this equation, and then when you multiply by the area, you'll find you got very interesting thing. Find phi after multiplying by the area. Let me just go through. What's flux? It's density times area. All right, let's take it step by step here. What flux density related to H? What's B equal to? Mu H times area. How you get H? You get H for Ampere's law. You know Ampere's law, HL equal Ni, right? So you will say mu and H from this equation will be equal to Ni divided by L. H equal Ni divided by L. Area. I want to leave Ni by itself, I call it magnetomotive force, F. So Ni, I will call it F. So F multiplied by mu A over L. Let's say F over L, and then instead of multiplying by mu A, you say L divided by mu A. So in the end, I find flux is equal F over L over mu A. L over mu A, I'm going to give it a name, reluctance, R. So in the end, you have phi equal F over reluctance R. This is similar to, we're trying to make it similar. There is analogy between this magnetic circuit and the electric circuit. Phi is like current, F like voltage, reluctance like resistance. That's Ohm's law. Then you make life easy when you analyze the magnetic circuit. So phi is like current, F magnetomotive force like voltage, and R reluctance, which is equal L over mu A. And as I told you before, in this universe we are living, everything's similar, the same law, but different variable names. Let me show you the reluctance. What's reluctance? Reluctance is the resistance to magnetic field to go through. All right. So we got R is equal L over mu A. Let me just write the reluctance of magnetic field. We just prove it's equal L over mu A. What is the resistance of resistance? It's either equal resistivity times L over A, and the opposite of resistivity, conductivity, and times L. Look at the similarity between that. And I can get you many different systems. You'll find they have the same formula. Reluctance proportion directly with the length of the core, what is the path. Resistance proportion with the L. Inversely with the area. Resistance inversely with the area. Inversely with the conductivity. Inversely with the permeability. And both are the same meaning. Resistance. Conductivity, it means how much electricity the material allowed to go through the electrons. Mobility, how much magnetic field allowed to go through the material. Same. Everything in the universe is the same. And that's called reluctance, and that's called resistance. Both are the same. So now, this magnetic circuit, we can make it simple by, we say, okay, this magnetic force, the coil, I will make it represented as a voltage. I call it F, and it's equal MI. And the reluctance of this material, of the core, I will represent it as a resistance, and they're called reluctance. And the magnetic field going through, that's called phi. I think it's the time to make an example, see how we solve this. And current. And there is magnetic line flux going through, but it doesn't go through all core. There is kind of gap. So with the gap, the magnetic field will air gap is really very small, like a millimeter, something like that. Why we are doing this very small? Big will have something I'm going to explain for why you find the magnetic field be like circles around. I want to keep it the same, going through the air gap, no disturbance in that. They call it fringing, like that coming out and make it like a bubble. We don't want this because it will make our calculation complicated. So let's assume it's very small, and it's gap is equal 0.5 centimeter. See the difference? It's 0.05 centimeters. No, it's just me. And the flux density in the air gap is 0.8 Tesla. That will produce this magnetic has density equal 0.8 Tesla. So we need to find the current. That's the first question. I. So I need you to tell me how we find the current. And that's given. Just look at what's given. Let me just write what's given. We need to find I. It's given in 200 turns, area 0.1 meter square. L is given, LC is equal 50 centimeter. LG 0.5 centimeter. Of course, everything has to be converted to meter. So that will be 0.5 meter And what else? Flux density is given B in the air gap is equal to 0.8 Tesla. We need to find the current. We got to go back to see what kind of relationship that it can give you the current. What current, what the effect of current? Just ask yourself this question and say, maybe it's not given directly and you make like 2 steps, but first, the current. What the current produce? What other variable related to current? With H. Okay, that's right. Current is related to H. But H is not given, right? What's given here instead of H? What things about magnetic field given in this problem? B, all right. So is there a relationship between B and H? Yes. So now we have hope. So the technique, the strategy in our mind, from B, we should get H, and from H, we get the current, right? Air gap, for the air gap, right? That's a good question. Oh, this. Let me just sketch it back again to keep the mass fun. That's if you have magnetic field going through here, and we assume that this air gap is very small, so the same line will go there. That's phi. So this is phi in the core, and this is phi in the air gap. And obviously, both are equal, is the same. There's no loss in it, because we're assuming it's a small air gap, so nothing will go out of it. What do you mean? I want to just let me go back to the other side. What does it mean if it's big or small? Yeah, here you go. That's what I mean. If there is no air gap, very, very small, you'll find all lines going in this direction. That's what we're assuming. If it's a little bigger, then you'll find something in the edge coming here. Call it fringing flux. Not so. In these two cases, we are not assuming it. We are taking this case. So in this case, the all lines going there because so small, nothing is escaping. So phi air gap is equal phi core. So we know from that assumption, the small air gap, that's phi C is equal phi G. And we have VG, as you said. We get phi G, the flux in the air gap. And if we got the flux in the air gap, we get the flux, the same equal to flux in the core, right? So now we have hope. So let's find how. First, I want to find the flux in the air gap. What is the relationship between flux and density? We just said phi. And what's the difference between B and phi? What is B? What's the density? The density is equal to flux divided by area. So flux is equal, that's what we know, that B is equal phi over area. So phi will be equal B times area. The area is given, but you say the area is given in general. Yes, because the area of the core is the same area that with the air gap. So both are the same. B is equal 0.8 Tesla, and the area is given in meter square. So we can get phi G in this case, which will be equal 0.08. What is the unit of flux? Weber. Uppercase W, small b. All right. H in the air gap. How you find H in the air gap? If there's a relationship between H and phi or B, okay, B general equal mu H, right? If you are talking about the air, so that will be mu naught only, and that will be BG, right? If we're talking about the air only. So, and mu is given, mu naught is equal 4 pi, it's constant, 10 minus 7. So yes, we can find H of the air, or in the air gap, you can call it G. It's equal BG over mu naught. We have BG is equal 0.8, and we have the mu naught is equal 4 pi times 10 negative 7. I get HG. It will be a big number. It will be 6, 3, 6, and that's 19. And the unit Ampere turns their M. That's the field intensity in the air gap. And I got everything because it was given the flux density in the air gap. Okay. But we are interested in the
0.08.
I mean
0.08.
we said, what's the relationship between B in the air, the flux density in the air, and the flux density in the core? They are equal. Why? Because we are assuming it's very small, right? So we say since the air gap is very small, okay, ion or core is the same as the air gap, the same value. So I need to find H of the. So how you find H using B is the same thing that we are using, but we don't have mu. We don't have mu. We got to find the curve to find it because it's nonlinear, as you know. So I have to go and get the curve. Yeah, I have the curve. This curve, let's take a picture. Silicon. Find H. And I already did that by looking at 0.8 Tesla. That's the B in the core. And then why I'm using this curve, because this is the material was mentioned. So I go down to look for the value of H, and that will give me the value of H. In the paper here, that H is equal to 250, I wrote here, 250 ampere turn per meter. So I got H. So if B in the core is equal 0.8 Tesla, HC is equal to 250 ampere turn per meter. I got H for the core. Right. You can use me if you wish, and you are asked find the corresponding permeability of this material of the core. You can do it now. You divide. If it's a question, say, okay, you know, B is equal mu H, so mu. Let me make it clear. Yes, mu core is equal mu naught and mu core relative. That's equal B over H. Because B, sorry, mu H, B over H, core. That's 0.8, and that's 250. I get the total. If you wish, you can get it. Like equal 0.0032. All right. That was extra. What I'm concerned with H. I got edges. Let's look at the problem here. Till now, I didn't get the current, but I got many things. That it will help me in the end. I got the B's, I got the H's. Now let's find the reluctance. How you calculate the reluctance in general? It's L over mu A. So if you want to find the reluctance of the air gap, it's equal L of air gap divided by mu naught only divided by area. And then you calculate it. LG is given 0.00, it has been meter. Mu naught is equal 4 pi 10 negative 7, and the area was given 0.1 meter squared. And then that would be the reluctance for the air gap. That's equal 3, 9, 7, 8, 9 Ampere turn there. How to find for the ion? The same thing for the ion, for the core will be L of the core divided by mu naught mu R, and we already got it. You can call it just for simplicity mu for the core, just mu of the core and the area of the core. Of course, area of the core equal the area of the gap, but I have to write it right. That was the length was 0.5 meter. We calculate the mu, the total, it was 0.0032, and the area is the same, 0.1. That's the reluctance for the material, 1563 Ampere turn per Weber. So I got both reluctance. Very easy. L over mu A. Five. Sorry, I want to find the magnetomotive force F. How you find F? We said it's like electric circuit, right? Let me just remind you. That's F, the voltage, and that's the resistance. We call it the reluctance, and that's phi. So what's phi equal to? Is equal the current times the reluctance. But the reluctance here will be equal to both. You add it's like adding resistance, the reluctance of the core plus the reluctance of the gap. So reluctance of the core plus reluctance of the gap. Phi is like current. The current in the gap, like the current in the core. And we calculate phi. Let me show you how we calculate phi. Remind you, we did that phi here. We multiply B times A. You told me about this in the air gap. It's the same. Oh. I got the reluctance. You add the reluctance, and after you add the reluctance, multiply phi that you got it, you get F. Once you get F, let me give you a number so we can, when you do it, Tom, it's equal 3308 Ampere 10. Remember, this flux you're going to use, it's the same air gap or cool. They are equal. And you get F. Once you get F, F is equal N times I. You have I. I was, no, I'm sorry, I was not given, but the number of turns were given. Let me check here. 200. N is equal to 200. So you have 200 N, you have F, the magnetic force, so you can get I. So I got it 16.5 amp. You have to have F. How to get F? Using the equation here. F like voltage, phi times R. So you have to have phi, and so on. I'll publish the document, and next time when you come, I will give you a problem and you're going to solve it in the class. Yes.
When is our quiz next week?
It'll be the end. Then it will be like on, you have exam Friday, right? So let's say you will have it Tuesday.
So we have a quiz on Tuesday.
Yes. Yeah.
Okay.
And
The test is on Friday?
yeah.